Imagine a demon that knows all laws which govern nature, and also where every particle currently is and what it's doing. If this demon had enough computational power to analyse all of this information, it would be able to see the future of the entire universe, down to the smallest scale, as simple as pressing fast forward.
But where the hell does chaos come from?
In the beginning was chaos, a vast gaping void, and out of this primordial chasm emerged the gods and our world. And out of this world emerged the type of chaos that we're actually going to be talking about in this video. Sorry, Zeus. Have you ever thought how things might have been different? Like, if you snooze your alarm this morning, maybe you'd be a bit later out of the house, and maybe a bit later crossing the road, just so that that car you saw speeding down the road actually ends up hitting you. And then you start thinking about how this goes much further. If your parents hadn't been in the same party that night they first met, or if your granddad didn't survive from the pneumonia he had as a child to meet your gran, or if your parents didn't do exactly what they did do all the way back to the beginning of humans and the beginning of life and the beginning of time, you wouldn't exist. We've all thought about this at one point or another, and it's closely related to a popular idea known as the butterfly effect. This possibly derives from a 1952 short story by Ray Bradbury in which a team of time travellers go hunting dinosaurs and accidentally step on a butterfly with dreadful repercussions for their future. He writes, "It fell to the floor, an exquisite thing, a small thing that could upset balances and knock down a line of small dominoes, and then big dominoes, and then gigantic dominoes all down the years across time." This idea that small differences at an earlier time can lead sequences of events to rapidly diverge is called sensitive dependence and is at the heart of chaos theory. But the official discovery of chaos theory was only in 1963. How can this be the case when the concept is so common sense and we've all thought of it? Well, physicists have been toying with this idea for a while. They just came at it from a different angle. A more physicsy angle. Physicists want to be able to predict things, and so they take measurements and formulate laws and build models. They want to be able to say that Halley's Comet will next be with us in 2061, and they want it to seem more like a fact than the words of Nostradamus. But more than eclipses and meteor showers, there is one thing that scientists are notoriously bad at predicting even to this day. The weather. Benjamin Franklin had been something of a trailblazer, noting the direction of travel of weather and then writing letters and sending them to cities ahead to tell them what was heading their way. The only problem was the postal service was slower than the weather. It was with the invention of the telegram that predictions started to arrive before the storms themselves. And in 1875, the first weather chart was printed in a newspaper showing bands of pressure and advising to wear galoshes. And while through the 20th century measuring instruments improved, technicians still relied on gut feeling and intuition in order to make their forecast for the next day. But this all changed with mathematician and meteorologist Ed Lorenz and a primitive computer called, and I kid you not, the Royal McBee. He was using it to develop a simulation of global weather patterns using pressure and temperature and wind speeds, and it was so revolutionary in 1960 that graduate students from around the university would flock to it and take bets on whether there would be cyclones or stillness tomorrow. One day, he decided he wanted to see a particular result again, and so he reran the simulation and typed in the same initial conditions. Except when he got the printout, it wasn't identical to the early result as it should have been. In fact, although the program was exactly the same, the patterns diverged rapidly. Lorenz quickly realised the difference. In his rerun, he had entered the value of 0.506 to save time, whereas the original run used the initial value of 0.506127. This minuscule difference of 0.000127 was not inconsequential, however. It changed the entire simulation of weather patterns. As Lorenz himself put it, the flapping of a butterfly's wings in Brazil can cause a hurricane in Texas. That is a bit of hyperbole, but it still attests to the unpredictability of weather and chaotic systems in general. And the thing is, we can never have 100% accuracy in our measurements. You can always have more gradations on the ruler and more digits after the decimal point on your weights. This is the refutation to Laplace's demon that we saw at the beginning of the video. It's actually impossible to have perfect knowledge of the positions and momenta of all particles in the universe because it's impossible to measure them properly. Therefore, We can't see the future even if the universe is predetermined. Because of the exponentially diverging paths that slightly different measurements predict, as time goes on, they become pretty useless. This is why to this day we still can't predict the weather just a couple of weeks in advance. Now it's time for some maths. As well as exhibiting sensitive dependence, chaotic systems are also described as non-linear. Linear is like y equals x. A straight line of some sort. You increase one bit, the other bit increases, same every time. No surprises. If you want to get technical, a linear system will respond proportionately to a change. So by contrast, a non-linear system doesn't, and will be typically described by a set of non-linear equations. A non-linear equation, for example, might look something like this, or this, or this. Yeah, a lot more complicated. Here are some examples of non-linear systems. A double pendulum, the moon around the earth, the stock market. You get lots of complicated and chaotic behaviour. In order to visualise this behaviour, we use a mathematical concept called the phase space. In phase space, every point in space corresponds to a unique state of the system. So if we take a linear, non-chaotic system, like a simple pendulum, which just swings back and forth forever, its phase space might look something like this, where the x-axis has the position and the y-axis the velocity. Every possible position the bob of the pendulum can be in as it steadily swings back and forth is on that line. It just goes round and round and round. Now let's use the same non-linear system that Lorenz had in his Royal McBee and see the trajectory that this maps out in phase space for one particular solution. It's a lot more complex than the pendulum, and if you follow how the system evolves over time, you'll see that it's never in the same state twice because the line never crosses itself. And if we change the parameters of the initial conditions slightly, this is the result. Completely different. So random. But is it random? Sure, these systems are going all over the place, but they're still deterministic. Cause still follows effect and nothing else. A random system is one where you don't change the initial conditions at all, not even slightly, and you still get a different result. This is what happens when a single atom radioactively decays, but this depends on your interpretation of quantum mechanics. Another way of thinking about it is that in a system with true randomness, even Laplace's demon wouldn't be able to predict what happens next despite knowing the positions and movements of all the particles. Day to day, when we use the word random, what we really mean is unpredictable, given that our measurement equipment and our knowledge and our computational power is less than perfect. Is something like the roll of a dice random? It appears so to us, but if we ask our demon, he'll be able to tell you based on the analysis of your wrist movement, the speed of the dice, and countless other factors that you'll roll a 4. It's still a completely deterministic process. James Gleick in this way described chaos as order masquerading as randomness. How long is the coastline of the British Isles? The answer is we don't know. How can this be? Well, more precisely, we can't know unless we specify one extra bit of information. Look what happens to the coastline as we decrease the size of the ruler. Suddenly, we're able to get into more and more nooks and crannies, which results in a longer and longer measurement of the coastline. We can imagine getting really up close with a microscope and measuring the tiny bumps on all the rocks around the whole country too. This is a real-life example of a fractal, mathematical object proposed by Benoit B. Mandelbrot. The B stands for Benoit B. Mandelbrot, by the way. Unlike mathematical fractals though, real-life fractals have limits. Zoom in enough and you'll hit atoms. Go out far enough and the United Kingdom will just be a speck. Other examples of real-world fractals are things like clouds and mountains. In mathematics, fractals are defined by being self-similar in this way, but also having fractional dimensions. This means instead of being 2D or 3D, they might have 1.7 dimensions or 3.24 dimensions or any non-integer number. All this tries to show is that as you zoom in, you get more bang for your buck in terms of detail. Now at this point you might be saying, fractals are pretty and all, but what the hell do they have to do with chaos? Well, if we go back to the phase space representations of chaotic systems and look at the trajectory plot of the Lorenz system, we actually find out that it has a fractional dimension of 2.0627160, slightly more than 2 dimensions. And you can see that it's slightly 3-dimensional. The periodic nature of the evolution of the system around 2 areas and never repeating gives it the name a strange attractor. Here are a couple more examples of attractors with fractal structures. Since gaining recognition in the 60s and 70s, chaos theory has worked its way into many diverse fields of study. Economics, robotics, astronomy, the weather, cryptography, the list goes on. Because while it is to some degree pessimistic about our ability to predict the future, paradoxically, at the same time provides us a model with which to better understand the world. So if you ever meet a demon at a crossroads at midnight and he tells you he knows what the future holds, ask him if it'll be raining a week on Tuesday. Thanks for watching. That was What the Hell Does Chaos Mean? Sorry it's gone up a bit later than usual this week. I've been at Sheffield Documentary Festival. We've got a couple more good videos lined up ideas wise. I think should stay tuned for the next one in 2 weeks. It's going to be a bit obscene, I guess. See you then. Bye bye.